Hey everybody, it's Jonas from tezos.community. We had an epic meetup last night in Menlo Park. Arthur spent about 2.5 hours talking tech about the Tezos blockchain platform and answering questions from the audience as well as from the Tezos community forums. I've taken the video and split it up into 3 or 4 different segments so that, frankly, YouTube can handle it. And I look forward to presenting those to you over the next week or so. Here's the first one. Apologize in advance for the sound. I will endeavor to improve my microphone situation for the next one of these that I record. But in the meantime, please visit us on tezos.community. We have some great forums there, and the website has just got a new refresh. So we look forward to getting your feedback and growing the Tezos platform together. Cheers.
I'm Arthur. I'm the tech lead on the Tezos project. This is Jill. Jill is, if you've seen the August updates, she's a new hire of the Tezos Foundation, and she's working on business development. So, rather than jump into it, I'm going to let Jill give a few words about the efforts in business development and what the foundation is up to.
Yeah, great. Thanks so much. Sorry for the delay getting started here, everyone. It's always a great test of your tech lead to see whether they can get the presentation slide deck up and running, right? So before Arthur jumps into kind of some of the technical things that the project is working on and thinking about, I figured I'd just give kind of a broader 10,000-foot overview of what's been going on. Probably many of you saw the August update. So I'm very happy to be on board Team Tezos, and that would also mean that you probably also saw our announcement around allocating 50 million of the funds that we've raised towards VC kind of structures to go towards building up the ecosystem and the broader community. So that means everything from, hardware wallet providers who might be interested in integrating with Tezos. Very happy to fund infrastructure like that to, if you're an entrepreneur or developer looking at decentralized applications that you would be looking to build on the platform, we're happy to hear from kind of all manner of people who are looking to support the ecosystem. On the other side of that, we've also been talking to, again, a range, from small individual entrepreneurs who are just getting off the ground in the space, all the way up to, kind of Fortune 500 status enterprises who are looking to build on a blockchain platform, and of course, we're looking to be that blockchain platform of choice. And again, this ranges everything from the financial services industry all the way into gaming and kind of virtual reality and AR kind of world of new asset classes, digital asset classes. So we've had some really exciting progress, again, over the last couple of months, just in terms of looking at new use cases and looking at new partnerships, et cetera. Probably most relevant to this community and anyone who's kind of tuning in as well is that we are going to be continuing to build out the team. So that's going to be, again, everything from the core protocol engineering team. If you are interested in OCaml, if you're a talented OCaml developer, definitely get in touch. It's a small, intimate community, and we're always happy to hear from you. But then that will also mean a product team, so we'll have people building out the developer toolkits, as well as people who are interested in building out kind of prototypes and demos as we, again, continue to work with bigger enterprises and have other partnerships get off the ground in the space. So lots of exciting things coming down the pipe as we prepare to update you all again in September with a more formal update. Look out for all kinds of announcements around that, as well as a revamped website. We know it's coming. So any questions, just find me after, or else find me on Twitter, or else find me on email, just jill@tezos.ch. Very happy to be here, and again, welcome. I'll hand it over to Arthur from here.
Thanks, Jill. Hi, everyone. So I'm just going to give a short presentation, and I don't want to be too long, and I do want to take a question from the audience because it's hard to know in advance what the audience is going to be, and I bet that there's a mix in the audience of people who are interested in the project for different reasons, coming from different angles, and so it's hard, it's hard to get a one-size-fit-all presentation for that. So I thought today I was going to talk a little bit about the state of the project itself as a piece of software, because one of the most important things we have to do is launch a live network, right? Right now we have a test net running, so you can play with it, you can deploy contracts, you can make mock transactions, but it won't be really real and concrete until we have the live nets going. And I want to talk a little bit about what it takes to go from where we are now to where we want to be before the launch of the network. So then I'm going to recap a little bit a blog post that I made a few months ago, which was the state of the Tezos ledger, and of course that state has advanced since then. But I think it's good to see where we currently stand. So the first thing I want to tell everyone is that if you are a developer, if you are interested in Tezos, one of the best things you can do right now is participate in the testnet and provide some feedback on your experience. So there's probably the best resource at this point for doing this is our Riot channel. So actually I say Riot channel, it's a matrix channel. So there's this new form of IRC called Matrix. It's an open system, and it has a client which is very popular called Riot. You can access it at riot.im. If you go to riot.im, you can create an account and join the Tezos chat room. So if you do that, you'll find a lot of people are using the testnet and they're discussing about it. We have some developers on there, and we're always happy to help you use it. And another good resource is the website www.mickelson-lang.com. This is a website which is done by one of the team members named Milo Davis, and he's been doing awesome work since September. And this is his personal blog where he's been writing a Mickelson contract every day. So it gives you a good sense of like how to deploy contracts. And at the beginning of the page, he gives you instruction on to how to connect to the testnets, how to use an Emacs mode for writing Mickelson, and how to deploy contracts on the chain. So this is really helpful resources if you want to get started. We're working toward doing a screencast that will show you all of that so that you can look at the video and say, hey, this is how we get from 0 to actually running running the testnet and deploying contract on top of it. Now, if I look at the state of the Tezos code, essentially, let me describe a little bit the code base. So far we have about something like 40,000 lines of OCaml in the project. So it's getting a little fat, and hopefully we'll be able to make it fewer lines, but that's not guaranteed. The projects tend to get larger, even though we try to keep them as concise as possible. So essentially there are 4 big parts in the Tezos code. One part is the utils. So it's in 2 directory, min utils, which is really the smallest set, and utils. And these, you will find modules here who do encoding and decoding function, hashing function, cryptographic primitives. It's everything that is being used by the protocol. It's kind of a standard library that is being built for Tezos protocols to derive on. So the general idea of a Tezos protocol is that it's a piece of OCaml code that can live on the blockchain, and if you just say, okay, I want to adopt a protocol, you will grab that piece of code, compile it on the fly, and run it. Now, we don't want that piece of code to include every single primitive. We don't want it to re-implement hash functions. We don't want it to implement signatures algorithm. So we try to put those into utils. And I think in the future, we will put more of these libraries into util. So in some sense, doing so is kind of a mini hard fork, because it means that some protocol which might not be valid, because it might call a library that does not exist, would become valid in the future. But it's a very small thing, because we're just saying, okay, there's more functions you can call on, right? And as much as possible, if something is very generic, we want to put it there. We don't want to re-implement cryptographic primitives. So that's the utils. And another part is the node. So the node, which we call the network shell in the paper, is a piece of software that runs, and it connects to other nodes, and it exchanges blocks, it exchanges transactions with them, and it tries to take these blocks and organize them And it calls upon the protocol to say, hey, protocol, I have these blocks. Which of them are valid? Which of them follow each other? Which of them, which branch should I be picking in order to decide what the current consensus is? So that's what the node does, and it's the most in some sense it's the most messy and complex from a programming standpoint part of the algorithm. The protocol itself, in terms of programming, is rather straightforward. There's some I would say technical, how would I put it? So if you write the protocol, most of it is applying logical rule. Now there's some subtleties around how you would implement a programming language. There's subtleties around your consensus algorithm, but all of these are, I would say, high-level algorithmic problem. Whereas writing the node is a real software engineering. It's much more of a software engineering challenge. So that's a node. We have a client. So the client is a directory. You'll find several clients. There's two which are particularly important. One is a command line client, which is it's a basic interface that lets you connect to the blockchain without directly calling RPCs, and you can use this client to say, create a new contract, send point to someone, and so on and so forth. It's very basic, and we're evolving towards making our client much more of a library than just a command line application, right? If you look at the way that the Bitcoin client is defined, this is pretty close to that. You call it and you pass some function and it does a few things. I think one of the insights that Ethereum had, which was a good insight when they built Web3, was to say, well, really our client should be a library, right? We should have this high-level interface library, and that way we make it easier for people to build clients using this library, either like traditional wallets or web clients directly on a web page. So I think that's a good insight. It's a good idea. That's something we want to do as well, and that's going to be still a work in progress. And the other client, which is also a tricky one, is the baker. So the idea of the baker, and just let me step back and why we call this thing baking. So in proof of work mining, most of your consensus is based on well, your consensus in proof of work mining is based on people solving these cryptographic puzzles by running a lot of computations and randomly finding near collision in hashes, right? So it's called mining because it's the idea that you expand resources and you dig and maybe you find something. And in proof of stake, you want to use a different word. So what word should you be using? So you could say, well, we'll use mining as well. But if you use mining, there's confusion. People might think that you're talking about proof of work. Now, another word that's been suggested was minting. And now the problem with minting is that it's a typo away from mining. And it also has the idea that you're creating coins. And there's been this tendency to think that the coin creation and the consensus algorithm were really tied. And I think it's very clever that in Bitcoin you get this block reward for mining, but it's not coin creation is not the essence of mining, right? The idea is like you don't need to mine to do coin creation. You need to do coin creation to incentivize people to mine, right? So I don't like the word minting too much. NXT, which was one of the early proof of stake blockchain, had the concept of forging. You forge a block like you would. I like the idea that maybe you have your big hammer and anvil and like you're forging this block, but forging has the idea of forgery. Maybe it's fake, so that's not a great word. And so this being a French project, we had the idea of baking, so that instead of blocks you have bread, and you can add yeast to the so hence the terminology baker. And if you read some of the Tezos documents, maybe in some places in the comments you'll find mining somewhere. There's no mining; it's all baking. So the baker is a client, and if we took a very extreme approach to protocol design, in principle you could produce a protocol and not write any code for the baker. You could just say, hey, this is a full node, and it just so happens that people will write clients in order to connect to these full nodes and get block rewards by being a baker. Now, obviously, we don't want to rely that much on external effort, and so we're building our own baker. So essentially, the baker is a client that looks for blocks and say, hey, is it my time to sign a block as a part of the proof of stake algorithm? If so, You know, I make sure I'm on the right chain. Okay, I'll validate the transaction, put them in the block, create my block, sign it, publish it on the network. That's what the baker does. Right now, I think the baker is a part of the code that needs a little more love. And if you've been running the testnet and if you've had a testnet sometime get stuck, I would say that 99% of the time this is mistakes in the baker code. So, you know, the baker I think started really getting to life around January, February of this year. And right after that, most of the team started working heavily on the security of the crowdfunding websites. So that took a lot of effort, and so we're getting back to the baker. So we should have a little more liveness into in the testnet going forward. And the fourth part of the code base is the protocols themselves. So there's actually 3 protocols in the Tezos code base. There's one which is interesting, which is the seed protocol, the one we're going to launch with. There's another one which is just a bootstrap protocol. It does nothing except grab the seed protocol and make it the main protocol. Right? So one of the cute things we might want to do is say that actually the seed protocol of Tezos is not a part of the Tezos code base. Right? You just have to download a much smaller one. But the first thing it does is look on the peer-to-peer network for the seed protocol and just deploy it. That's just because it's cool. You know, there's no need to do that. And there's also a minimal protocol which I think has a very simple proof of I think it's a very simple proof of work algorithm. It's called demo, and you can look at it, and it gives you some sense of what the bindings are and how to write a protocol from scratch in Tezos. Now, to be honest, I don't think that, I mean, unless people are trying to launch competing blockchain, I don't think anyone is ever going to write a protocol from scratch in Tezos and propose it as an amendment, right? I think every amendment are going to be basically incremental rewrites of the seed protocol. But in theory, it's possible, and I think it gives a good sense of where things are. Now, we have different challenges in these different parts of the code that I mentioned. I think right now the greater ones are going to be in the network layer challenge. So essentially, there's 2 challenges for the network layer. And sorry, when I mean the network layer, I'm talking about the part of the code that communicates with other nodes, that grabs blocks, that tries to arrange them together. So the two big attacks that we have to worry about, one is spam and denial of service, and the other is Eclipse attacks. So Eclipse attack, an Eclipse attacks in a network is when you're in a peer-to-peer network and somehow someone manages to convince you to only connect to some of their nodes. So you think you have many different peers, but you're talking to the same person. And now that's a problem in every network. That's even a problem in a Bitcoin network, because you could have an Eclipse attack and you could think that you're getting all the blocks, you're getting all the information, but really you wouldn't be. So let's say you're a Bitcoin miner, someone could connect to you and say, hey, and not show you the real chain. So you would be building on some fake chain. Or if you're a payment processor, you could be isolated and somehow not realize that you're not connected to the main blockchain and see a fake blockchain. Now, one of the nice properties of proof of work is that in an Eclipse attack, you have some level of protection, because the chain is going to look weird. If you're a miner, you're going to see that the rate of block creation is off. If you're a customer, you're also going to see that. And that's partly because the difficulty of Bitcoin adjusts slowly. So that's one of the advantages of that slow adjustment schedule. In principle, how many systems are actually designed to monitor the hash rate when they connect? I don't think that many of them actually do so. And the problem with Eclipse attacks, so it's compounded a little bit in proof of stake, especially if you haven't connected for a long time. You know, connecting to the network, you would want to make sure that you are connected to some real peers. And one of the difficulties is that Bitcoin relies heavily on, well, I don't know how heavily, but it does rely on the IPv4 subnets. So it tries to look at the IP addresses and make sure that it's connected to many places around the world. So it's definitely, so we don't have this, we're thinking of adding that. The reason we didn't build it at first is that it felt a little futile, because we're moving to IPv6, so a longer format for IP addresses, which does not have this property where you can tie the address geographically as easily. It gets very, very cheap to create a lot of IPv6 addresses. So banning peers based on their IP addresses, or trying to make sure that they're diverse by looking at the IP address, it might work a little bit now, but it doesn't feel like a long-term solution. Yes?
I respectfully disagree, Arthur, because all registries like RIPE, ARIN, and the other registries have the IPv6 addresses in them, and you can always see which company is announcing.
You can,
Yes, I can
but
see
can you tie them geographically?
Yeah.
The same way that.
Same.
All right. I'm going to trust you on that. So I guess I'm conflicting information, but okay. So then, if that's the case, that is absolutely great news. My understanding was that it was much trickier, but okay. So the way that we try to approach the problem is essentially we try to give every peer an identity, and the way we do that is every node that connects to the network has to solve a very, very small proof of work just to create a public-private key pair. And whenever you connect with another network, it's going to be encrypted and authenticated. Right? So you cannot spoof other nodes, and when you spoof to a node, and nodes are going to have these like long-lived identities, which lets you build some reputation to them. So you can try to find nodes that can have some reputation. So that might be a good way of avoiding Eclipse attacks, because if you know that you're connected at least to 3 honest nodes, then maybe you don't fully trust them, but you know that you have some diversity in the node that you're talking to. Now, the hardest problem is actually the DOS attacks, and in particular, we're concerned with denial of service at the application layer. So there's always a possibility that someone is going to send a ton of network traffic to your host, and we're not going to try to defend against that because it's out of scope for us. There are services that can defend against that. Maybe your operating system has ways of defending against that. But we're mostly concerned with people trying to spy on your node by, either the proof of work is invalid, but that's extremely cheap for me to check that. So I'm going to check just the hash of your block. I'm going to hash your headers, and just with one hash function, I know if your block is made up. And sure, you could make a block, but it would be extremely expensive to make enough blocks that would actually cost a significant computational effort on your adversaries. So that's a nice property of proof of work. What can we do instead? Because if by definition it's very cheap to create blocks, you could flood people with invalid blocks, or you could say, you know what, you have this chain, here's a very long chain reorganization, validate it, and I promise to you that once you validate it, you will find that it has a higher weight than your current chain, and you should do a reorganization. So you could have a substantial computational effort in doing so. So we have several mitigations to that. One is that we have a layered approach to chain validation. So when we validate a new blockchain, we do by default 3 passes. And what those 3 passes do depend on the protocol. It's just the idea that you'll do, you'll have first, you'll just look at the minimal headers of the blocks, and you'll try to decide if you see something invalid. What do we have in those minimal headers? Timestamps, the fact that a block has a hash and has a predecessor, and we also put a tiny proof of work in every block. So does that make us a proof of work blockchain? No, because there's not a race. There's not like a Red Queen effect where it's always going to be more and more expensive to do proof of work. The idea is that there's a small proof of work which is about on the same order of magnitude as validating the block. So the idea is that if I'm making you validate a block, at least I spend myself the computational effort to create it, which is similar to validation. So we're still talking like orders and orders of magnitude cheaper than creating a Bitcoin block. So timestamps, a small proof of work stamp, those are the first layer of defense. The second layer of defense is that we're going to check that these blocks in a proof-of-stake algorithm have been signed by the right people, that the signatures are valid. Now that can be pretty fast as well. It's a little slower than checking a hash, but it's still relatively fast. And then the last part of the checking is actually checking that all the transactions within all the blocks are valid. So this 3-pass validator is a work in progress, and it's going to be, I think, one of the most important defense against this type of attack. The other defense that we have is doing some peer reputation. So if a peer ever sends me bad transactions or bad blocks, then I will block out this peer and not talk to it, and I can exchange blacklists with other nodes. If I'm another node, I'm not going to trust directly a blacklist because I don't know where it's coming from, but I can get information from it. And in general, you can think of the network layer as a mini economy where some sort of debt-based economy. So, if you're a new block, I don't know you, you don't have a lot of credit with me, so it's going to be hard for you to force me to do computation. You might ask me, hey, send me a lot of blocks, validate all these blocks, but I'm gonna slow you down. I'm gonna pay attention to what you're saying, but I'm also going to pay more attention to what the other peers are saying. And progressively, the longer you've the longer you've been exchanging information with a peer, the more you trust it, and the more you're going to be willing to give that peer some of your computing resources and bandwidth resources. Yes.
How do you plan to, I guess, track and calculate that reputation? Like, what's that based off? Just history?
It's just based on history.
Okay.
If you've sent me a lot of blocks in the past, then you've given me a lot of bandwidth, and I should be willing to give you a lot of bandwidth as well. Right? The idea is that you could create a node and then try to like forge a long history with someone of trust, and then spam them by sending them a fake block. But it will take you much. It will be much faster for you to lose all your reputation than it would be for them to gain it. Now, one solution that we haven't done, and we won't do that for the first version of the protocol, but I think it's an interesting one, is to do on-chain node registration. So some blockchains call this master nodes, and I'm not necessarily a fan of those blockchains, but I think the idea of saying, hey, if you're a full node, you're going to have some identity that's on a blockchain is interesting. And it reminds me a little bit of proof of stake, in the sense that in proof of stake, you use the content of your ledger to actually power your consensus algorithm, and here you use your content of your ledger to protect your network layer, right? So if you could have full nodes be bounded on the blockchain itself, you could be in a situation where, say for example, you receive a fake block from that person and it's signed. You could publish it on the blockchain and say, hey, this node actually is a liar. This node didn't actually relay the right information, and they would lose the bond. So I think that's an interesting layer of protection, but it does add some complication. One very simple thing you can do is, since we know that there's going to be some like big bakers and big validators, they will be running full node, is to be sure that they are, in your peer list you have some of these full nodes. To avoid the eclipse attack problem again. So on the protocol layer, the challenges we have are currently around, I would say, two categories. One is the data storage. So every smart contract is storing data, and I think when Tezos was in its infancy, the smart contracts were thought more as some type of more advanced Bitcoin script, right? Let's have Bitcoin script, but let's be able to be a little more flexible about what we're doing. Let's be able to have state. And so I think it was assumed that the storage that the contracts would have would be very small, right? In Bitcoin, you essentially have a 1-bit storage, which is this output spent or not spent? Whereas in a smart contract system, you could have integers, you could have strings, you could have something bigger. And I think that Ethereum has demonstrated that there is some value in having contracts with potentially very large storage. And those contracts are the ERC20 contract, where you have this huge map that maps out addresses to balances. And so that's an important use case. And there's two ways we can make sure that we support this use case. Because right now, if you use the current blockchain, what it does is when you run a contract, it will deserialize the entire storage, work on it, and then reserialize the entire storage. So if your map, is 100 megabytes, you wouldn't want that to happen every single time. So one quick hack we can do is essentially to have a special case for maps, because hey, we know there's one use case where we need a lot of storage, and we don't know many other use cases. So we have like a special map map type, which will have different costs of retrieving data. If we want to ship quickly, that's probably the fastest thing we can do. And so I think depending on the timeline, we'll do that, or the second solution I'm about to present. The second solution is a technique called hash consing. So the idea of hash consing is that whenever you represent data structure, especially the way that or functional data structures, you can represent them as essentially trees. So maps are balanced trees. You can represent a list as a sort of trees, pairs, and so on and so forth. So the idea is that every leaf, which is a data type, you can hash the value of that leaf and put it into a hash table. And then, let's say that I have two leaves, I have two values, and I want to create a pair with these values. So now, you put in a hash table that you created a pair out of two hashes, and the hashes represent the content of the leaves. Now, if you keep doing that, you find a way of storing your data such that if you have two pieces of data anywhere in the system that are the same values, they're going to be shared. So the nice thing about this is that if I'm a smart contract and I have this huge map, I could copy this other map to some other smart contract, and it wouldn't take any more space in the ledger. It would take exactly the same amount of space because it would overlap. And even if one map were slightly different, the way that you update the tree can be made such that actually almost all of the leaves of the tree would be the same and the storage would be the same. Like the difference between the two would be on the order of log of n. So that's a very powerful technique. The difficulty with it is it's trickier to implement. It requires us to design some sort of garbage collection that will happen at every block, and it needs this garbage collection to run in constant time. So there's some algorithmic work to do behind it. But one of the cool things we can do if we have this is it gets us libraries for free, right? Because if we store our data like this, we can also store our smart contracts. And if you store smart contracts in this way, then all of a sudden, if your smart contract wants to use a function that we're using in another smart contract, rather than making a call to the other contract, you could just copy paste the code. And as long as you have the same lines of code, it's going to be stored in exactly the same way in the ledger, and so you won't have extra storage cost. Now, the main difficulty with hash consing is actually figuring out how to charge for it. And so I call that the buy or rent problem. So when you have data on a blockchain, you're costing money to people. You're costing money because they have to store, they have to do some work the first time to store it, and so the state of the ledger is bigger, but the state of the history of the blockchain is also bigger, right? So what should you be paying for? Should you be paying for the state you're currently occupying in the current state, or should you pay forever for the state that you once occupied on a blockchain? So the buy model is to say that whenever you buy, whenever you use data on the blockchain, you have to buy it, and even if you remove your data, you're not getting your money back because now it's part of the blockchain. Now that might seem like a good idea, and the problem with that is that you don't have an incentive to actually clear the state, because we do want to reimburse you. So maybe we want to reimburse you partially. So you pay a cost first, and then you're partially reimbursed. Another idea is a rent model where you pay first to put it on the blockchain, and then for every block where you're still there, you have a small fee which is applied to the contract. Right? So the idea is that it works as a cleanup mechanism, because if you have a very old contract that no one is using, it's paying its fee at every block, a small fee, and then at some point it disappears. Now, we wouldn't want to do that with default contracts, which are just like balances, so that if you're just holding a balance and you just want to sit statically on it, you don't want to have to worry about rent, you don't want to have to worry about anything. So we're going to make it a special case. Combining how to make people pay for rent or buying the space and combining the idea of hash consing gets really tricky. Because if I put some data out there and someone else copies the data, now by copying the data, should they be paying something? Well, they didn't really add any more information to the blockchain. We don't want to charge them too much, because otherwise they'd have an incentive of maybe not copying the data or getting slightly different data. So if we charge them nothing, the problem is then they don't have an incentive to ever clean up their state. Once you have two people who share the value, how do you give them each an incentive to clean up the state? One thing you could do is say, I store a piece of data, I pay 1 TES. Now you store the same piece of data, all of a sudden you have to pay 1/2 TES, and I'm being reimbursed 1/2 TES. Right? So now we each have an incentive. So you could say that you could distribute the cost between everyone who's sharing this. Doing this in an efficient way with the data structures that we have is really tricky. So whether or not we're capable of implementing this will depend on the other efforts, but I think it's something to look into. In terms of, yes?
This is stepping back just a minute about the peer reputation thing, but
yeah.
I'm curious if you're building reputation of the nodes themselves, then the idea that eventually you could have effectively like trusted nodes would start to emerge. And so when you have like a series of trusted nodes, would reach a consensus faster because you have these C3 nodes that would be more trusted than others on the network, and therefore you can trust that the transactions are being validated by those peers with high reputation.
Yeah, so you have to make a difference between just the full nodes, which are just nodes that validate the chain and just like transmit blocks, and the nodes that actually create blocks.
Okay. So
in proof of stake, the fact that you know in advance who's gonna create blocks does give you a way of getting faster consensus, because you can send your transaction, instead of broadcasting your transaction, you can send your transaction directly to the person who's going to create the block. Now, some people say like, oh, that means you can be DDoSed because if people know you're gonna create this block, they can DDoS you. But that's not quite true because you can have you can change that address. People don't have to know like where you're going to be sending the blocks from. Right? They just have to know where. You could have one address where you're getting transaction from, and then the blocks themselves come from a completely different address.
Could it also mean that, and this could be just wacky and a stupid idea, but could it mean that nodes with high reputation, could they collude? Yeah, so part of the problem is that I believe that there are few trade-offs in blockchains. Sometimes say, oh, having smart contracts is nice, it's flexible, it gives you more surface area for attack. I don't really buy most of these trade-offs. So one trade-off I do buy completely is that there is one between how efficient you are and how decentralized you are. And it's not just like fully centralized, you're efficient, and decentralized, you're inefficient. It's a complete continuum in between. And so if you wanted to be resilient to DDoS, one way that you could be resilient to DDoS is by having much less information in blocks, doing much less, having this capacity. Another way you could do this is relying more on trust, on saying like, hey, we know these nodes don't lie, and so on and so forth. But in that case, yes, you introduce more risk of collusion. Yes.